Here we have a few applications of non-standard cell potentials and the way we can think about the Nernst equation. So the standard cell potential for this reaction, copper metal with the permanganate ion in acidic solution, is 1.34. If I make some changes to concentrations, is that going to increase or decrease the voltage? So we see that we decrease, or we have a low value for our copper, a product. We increase and we have a higher concentration for permanganate, our reactant. So since the reactant is increased and the product is decreased compared to the standard 1 molar of everything, remember, that decreases the value of Q, a small number on top, a big number on bottom. So we could do this in terms of the Nernst equation. The negative log of a number less than 1 is a negative value. A cell potential minus a negative makes it positive, and that's an equation or an argument that makes sense to a lot of people. Or the reaction driving force makes sense to others. The extra reactant, I now have more of this, and I've removed some product, drives the reaction more forward, increasing the voltage. It becomes even more favorable in the forward direction because of our relative concentrations. However we're doing this, we're thinking not that we're at equilibrium, but the reaction keeps going and pushing forward until it reaches there. And we're farther from equilibrium when we do this balance. The second example here has a standard cell, our favorite one, and our first one, zinc and copper. For each of these scenarios, think about what would happen to the voltage. So we bump the cell setup, the salt bridge no longer is in contact with the solution. What happens to the voltage? Does it go up, down, or equal to 0? In this case, it would equal 0. If you don't have a salt bridge, you don't have a complete circuit. But you want to go beyond just saying that. We don't want to just say, well, it's not connected. That would mean that charge would be building up in our cells, so the electrons can no longer flow. That is what it means to not have a complete circuit. But we would want to explain that we understand the role there, that the ions can't flow into solution, balancing out the charge. The student, same person, continues to run that battery overnight and then reads the voltmeter. Does the voltage increase, decrease, or equal 0? It decreases. And we don't want to just say, well, the battery dies, although that is what happens. And we know that from our personal experience with batteries. As the reaction proceeds, reactants are used up, products are created. This increases Q, a bigger number on top and a smaller number on bottom. It's now closer to whatever our K value is. The concentrations of the reactants decrease. That decreases the drive of that forward reaction. And we can also connect it to the Nernst equation by saying that bigger Q, we're taking whatever our voltage is, and we're actually subtracting a number away because Q is greater than 1, and the natural log of a number greater than 1 is a positive value. So all those are good arguments, but just making sure that you're confidently and correctly choosing one of those arguments.